Hear me? All right, so I would like to thank the organizers, excluding myself, for giving me this opportunity to talk, and also for arranging my talk right after Sanjib's, which has solved a lot of my problems. I'm going to talk about a first passage time problem for tracers and homogeneous isotropic fluid turbulence. I will define all the words in the title soon. I mean, my greatest surprise is this problem, as far as we can tell, had not been done before. So we'll tell you about it. The people who have done all the hard work is Akhilesh, who's there, and Akshay for their PhDs, and Dhrubaditto, and their current addresses are given there, support from these funding agencies, and we have a paper on the archive. So here's an outline of the talk. First passage time problems, this you already heard about. Then fluid turbulence with Lagrangian tracers, direct numerical simulations, etc. So as you learned in the previous talk, first passage time is a very, very old problem. There are lots of good texts. I've put two up here. There's a whole book by Prerna, and then there's a wonderful book by V. Balakrishnan on elements of non-equilibrium statistical mechanics. Please look at chapter 10. So as you saw, first passage time problems occur in many systems, random walks, etc. And let me just define it in the case of a Brownian particle in one dimension. Say it starts at point x naught, and the first passage time t is the time at which the particle reaches some point x, which is not x naught, for the first time. And that variable t then is a random variable, and you just learned that it has a full probability distribution function, p of xt x naught 0, and this gives all the statistics of t, and it is also related by a derivative to the survival probability that the Brownian particle has not reached x until time t. And this PDF can have many different types of things. So let me tell you a little bit about fluid turbulence. Fluid turbulence is this crazy, chaotic motion of a fluid at high Reynolds number. You can see lots of interesting things. For example, you can see vorticity tubes. And if you look at this old paper, you will find that particles go to the core of the vortex. You also see these vorticity tubes in very high resolution simulations. This green forest, if you zoomed into it, you would see tubes of high intensity vortical regions. And then, of course, all of you who have suffered through any polluted city anywhere in the world will know that particles are advected by turbulent flows. So you see pollutants here, you see a volcano going off here, and the ash from a volcano can decide whether your flight takes off or not. You can study these tracers in a controlled way in a lab. This, I think, is from the lab of Eberhard Bodenschatz. And you have to contend with particles in clouds if you want to understand rain, which somebody like Samriddhi will do one of these days. Okay? So it's a very, very important problem. That's what I want to tell you. And so any information that you can get on the statistics of particles in turbulent flows has a direct bearing on these problems which affect our lives every day. All right, so here I'm defining a problem in the context of fluid turbulence. It says, consider a Lagrangian tracer particle. That's a neutrally buoyant particle which is used to track a turbulent flow that emanates from a point source in the turbulent fluid. And let t sub r be the time at which this tracer, initially at the origin of a sphere of radius r, crosses the surface of the sphere for the first time. Then we ask, what is the probability distribution function p of t of r? And this is obviously a first passage problem, which you heard about just now. And first, to give you the answer from our direct numerical simulations, which I will tell you how we do, we find that there are two distinct regimes. If the radius of this sphere is less than what's called the integral length scale, I'll tell you what the integral length scale is later, all right? Then we find a power law dependence of P on PTR, TR to the minus alpha, and with exponent alpha equal to 4. And if this radius is much larger than this integral length scale, then PTR has an exponentially decaying tail. All right? How do we get this? We get this by solving the Navier-Stokes equation, incompressible. All of you know this. U is the fluid velocity, P the pressure, nu the kinematic viscosity, F the external forcing. And then we know how to solve it. We are talking of homogeneous isotropic turbulence, so we use a periodic box, we use a pseudospectral code, etc., details that nobody except the experts need know. And these are the parameters. It's a semi-respectable Reynolds number. And to show you that the fluid is turbulent, I have plotted here for actually a low resolution run. We have the higher ones too. The so-called energy spectrum versus K on a log-log plot. The red is the measured value. The black line is the celebrated K to the minus 5/3 phenomenological theory of Kolmogorov in 1941. So with this sort of a turbulent fluid, we put in the particles. How do we put in the particles? These are neutrally buoyant tracer particles in the turbulent flow. The conditions under which this equation holds are given there. So basically dr dt is u, where u is the Eulerian velocity of the fluid at the point r. Okay, that's what a Lagrangian tracer is. Given this, given a computer, given a very good student like Akhilesh or Akshay, you can then obtain the probability distribution function. It is more useful to plot the cumulative or the so-called complementary cumulative probability distribution function, basically the integral of P. And here is a plot of Q, which is this cumulative PDF, versus some scaled time T. And the way we have scaled things, everything collapses onto one universal curve. And the dashed line is this power law that I alluded to. You can see this better than I. It's a power of minus 3. So by the time I take the PDF, that will become the power of minus 4 that I had advertised earlier. So they're real data, okay? And from many different runs, many different values of R over L. But I want you to note that all the values I've put up, the radius is less than the integral length scale. Now, if I let R become significantly larger than the integral length scale, then this same cumulative PDF, now it's a semi-log plot, so a straight line is an exponential, and so it's become an exponential. All right? Okay, so that's a discovery. Well, I hope nobody else had made it before. We couldn't find it. We did a good literature search, probably Samriddhi knows some papers, but somehow it wasn't there. Now, normally, most of my fluid turbulence talks end here because I don't understand turbulence. I have no way of understanding this complicated set of things. But it turns out in this particular case, we can actually come up with a simple model which helps us to understand this crossover from a power law form to an exponential form. And I'm just mentioning something here which I won't cover today, that we have obtained similar results for tracer particles in superfluid turbulence also. So let's look at a model that many people have put up before me today, the Ornstein-Unlenbeck process. This is standard, so I won't even go through it. All of you know this better than I. Okay, the mean value of the noise is this, Gaussian white noise, etc. And so you can then do the same calculation for this stochastic differential equation, all right, and obtain the same Q versus T. Now, I'm not giving you every detail, but in terms of these parameters, little gamma, capital gamma, m, etc., you can define suitably scaled times, which are plotted here, and there's a cumulative PDF. And this is in the regime where R over L is much less than 1. Given that we have a very simple model now, we can go to much smaller values of R over L than we could earlier. All right, and here's the same minus 3 power law. And if I let r become greater than L I have not defined, but it can be defined in terms of the parameters of this simple model, you get an exponential form, okay? But still it's numerics. So it turns out that if you're Akhilesh, you can come up with a simple argument, all right? And the essential insight is the following, that for small separations, okay, the particle basically moves ballistically. So the time tr is r divided by v, where v is the probability, excuse me, the velocity. And so you can relate it then, this p of tr becomes an integral of this delta function, pv dv. Now, little pv is the distribution function for the velocities. All of you know who've done turbulence know that the Cartesian components of the velocities are distributed more or less like a Gaussian. Therefore, the modulus goes like a Maxwellian, which is here. You put it in here, do the integrals, and then you look at the dominant term here, and in d equal to 3, lo and behold, r cubed over tr to the power of 4. That's the power 4 that we saw earlier. And then in the other limit, for large separations, the particle motion is diffusive, so you can solve this type of Fokker-Planck equation, which we heard about in the previous talk. I won't bore you with details. You know these things. I mean, people, the real experts are in the audience. So you get this form, and then you can write down the survival probability, which you heard about earlier. And the dominant term then just turns out to be this exponential. Okay, this is with absorbing boundary conditions at the surface of the sphere. All right? So here are the conclusions. We have defined, as far as we can tell, a new first passage time for tracers and turbulence. It crosses over from a power law to an exponential when we do the numerics. And then we can actually develop stochastic models, etc., which help us to understand these different regimes. So I thank you for your attention. Questions?